Welcome back. In this video we're going to discuss the law of cosines, which is a generalization of the the Pythagorean theorem. This law of cosines is a fundamental tool used to establish the cosine formula for the dot product. Let's go ahead and take a look at the statement of the law of cosines. If we have the lengths of the sides of a triangle labeled as A, B, and C, where C is the length of the side opposite to angle theta, and angle theta doesn't necessarily have to be 90 degrees. Here we have maybe not a right triangle, in fact generally not a right triangle. You have lengths A, B, and C, and then C is the length of the side opposite theta. In this situation, there's this beautiful mathematical rule that says, or formula, I guess, that says that C squared, the length of this side squared, is equal to the sum of the squares of the other sides, a squared plus b squared, minus 2ab cosine of theta. Notice that this is indeed a generalization of the Pythagorean theorem. If this angle was 90 degrees, then C would be the length of the hypotenuse, and then cosine of 90 is 0, and you have the Pythagorean theorem. Pretty beautiful, right? We're going to go ahead and prove this theorem, and we're going to do so in two cases. The first case we'll do is the acute case. I'm going to call the second case case 3 because it corresponds to the obtuse case, and this goes back to an earlier video in lesson 3 where we had these 3 different cases of the dot product. Case 1 was acute, case 2 was a right angle between vectors, and case 3 was obtuse. Okay, let's start with case 1. And in case 1, to establish this result, we're going to look at the following diagram. Here we have our angle theta. We have C as the length of the side opposite to theta, and then we have A and B. As stated, there's no ability to apply the Pythagorean theorem, which is the theorem we know and love about triangles, because there's no right angles. But if we drop a line down so that this line forms a right angle with the side length A, and then we call the length of this line H being the height, and then we call this piece X, this whole side is A, so then this would be A minus X. We know by the Pythagorean theorem we know two things. Since this is a right angle, we know that B squared is equal to X squared plus H squared. And we know that C squared is equal to A minus X squared plus H squared. Okay. This means that C squared is A squared minus 2ax plus x squared plus h squared, and this just came from expanding that square. But look at this. This is x plus h squared. We know by this statement that that must be b squared. So now I have a squared minus 2ax plus b squared. So this means that c squared is equal to a squared plus b squared minus 2ax. But we can have a side note here. If we look at the angle theta, the cosine of this angle is the ratio between the adjacent and the hypotenuse. In other words, cosine of theta is the ratio between x and b. Another way to say this is that x is equal to b times the cosine of theta, which means everywhere we see an x, we can substitute b times cosine of theta, but this is the exact thing that we wanted to show in our law of cosines. Cosine of theta. This is the statement, or the consequent, of the law of cosines for the acute case. All right. So now we've just established the acute case of the law of cosine. Let's move on to the obtuse case. All right. So in the obtuse case, let's take the following diagram. As written, we see that C is the length of the side opposite theta. We've got A and B. There's no right angle here, but we can construct a right angle by drawing a vertical line straight down onto this one, so that this is a 90-degree angle. We'll call this X, and we'll call this H. And notice that if this angle is theta, this angle would be 180 minus theta. And you could call that pi minus theta if you were excited about life. We might do that later in this video. And we have some interesting realizations with this in mind. We see that by the Pythagorean theorem, we have the relationship a plus x. I guess we could start with a small one. We see that h squared is equal to, b squared, this is b, right? B squared is equal to x squared plus h squared. And, so that takes care of the small triangle. And then we have the large triangle, right? The hypotenuse of the large triangle is c. And then we've got something like a plus x squared. So that's this side plus h squared, which is this side. Let's go ahead and take a look. So now I've got c squared is equal to a squared plus 2ax plus x squared plus h squared. Just as before, this here becomes b squared. So now I have a squared plus 2ax plus b squared. And this, of course, is a squared plus b squared plus 2ax. And we have a side note here. The side note that we have, so let's go ahead and look at this. We see that the cosine of 180 minus theta is the ratio between the adjacent and the hypotenuse. So here we have the cosine of, I don't know, might we call it pi minus theta? Is the ratio between x and b, right? The adjacent over the hypotenuse. Okay? And this means that x is going to be b times the cosine of 180 minus theta. And this is where we need to do some work from our pre-calculus careers. Recall from pre-calculus, cosine is an even function, which means that the cosine of theta, of course this should say theta, this is pi minus theta, the cosine of theta is the cosine of negative theta. And the way to think about that is when I draw the cosine, remember that the cosine is centered around 0 and it goes up from goes from 1 to negative 1. If I move positively in my domain, I get this very beautiful cosine curve. And it's periodic and it goes up and down. I love drawing the cosine curve. It's one of my favorite curves to draw, right? You go down here, it's pi over 2, pi, 3 pi over 2, pi. This is a positive orientation, which means I'm going this way in my domain. And the crazy thing is, reversing my domain orientation produces the same output. So if I do the exact same thing but in opposite direction, I actually get the same output out, right? That moving this way is identical to moving that way. That's another way to say this. Well, remember then what happens when we add 180 to negative theta. And perhaps if we're getting really excited about life and math, we stay in radians. Do you remember what we did when we added a certain value to a graph? Right? We ended up shifting that graph to the left or to the right. Do you remember? I'll leave that as an open question. In this case, it actually doesn't matter if you shift to the left and the right. You're doing one of them. When you add an angle, you shift this graph either left or right. I'm going to let the viewer figure it out for itself. But what I wanted to show you was that when you do that, you actually get a phase shifted cosine. When you shift this thing by pi, you get the negative cosine of theta. Because you're getting a shift of pi radians. Which means when you look at this relationship, everywhere I see a a pi minus theta, I can substitute that with a negative cosine of theta, which is negative b times cosine of theta. Oh, I guess there's a little hint if you wanted a hint on this. Think about when I do the absolute value of x plus 1. So this is a hint on whether or not it shifts left or right. Absolute value of x is the flying v function, right? The 0 of the absolute value of x happens right at the origin. And the question is, where would the 0 of the absolute value of x plus 1 happen? Well, the 0 would happen when the inside was 0, which happens this way, right? So adding 1 shifts the graph to the left because the 0 happens sooner. Can you guess what happens up here? Anyways, the whole idea of this is that we have x equal to negative b times the cosine. If we go back to our original analysis, we saw that this is what came out of the obtuse case. And then we just saw that x could be substituted with negative b times the cosine of theta, and this was the exact relationship that we hoped for in the law of cosines. All right, we've just finished our proof of the law of cosines by proving both cases. In the next video, we're actually going to combine our knowledge of the law of cosines with our knowledge of the algebraic properties of the dot product in order to derive the cosine formula for the dot product. See you in the next video.